Right then, what we need to look at next is electron pair geometry versus molecular geometry. There is a difference. What we've been talking about so far is the arrangement of the regions of electrons around the central atom. And I'm going to put pair in parentheses because we're really talking about regions of electrons around the central atom, not just pairs. Versus the arrangement of the atoms around the central atom. That's what we're really mostly concerned about, is the arrangement of the atoms around the central atom, and less concerned about the electrons. So if the central atom has lone pairs on it, one or more lone pairs, the lone pairs will affect the arrangement of the regions of electrons on the central atom. But the result of the lone pair is that there's kind of what you might consider an empty space around the central atom. That is, a space around the central atom where there is no other atom on the outside. Okay. And basically, the arrangement of electron pairs on the central atom will be different from the arrangement of the atoms if the central atom has lone pairs. We've been looking so far, vast majority of the time, at cases where the central atom has no lone pairs on it. Okay, so for SF6, the electron arrangement around SF6 is octahedral, and the shape of the molecule is octahedral, because every pair of electrons around the central atom, the sulfur, has an atom on the other end of it. But if there were a case where there was a pair of electrons on the sulfur that didn't have an atom on the other end of it, well, then the arrangement of the electrons would still be octahedral, but the shape of the molecule for which we only count atoms would be different. So straight away, we can say that if there are no lone pairs on the central atom, then the electron geometry and the molecular geometry will be the same. The same name. If there are lone pairs on the central atom, though, the electron geometry and the molecular geometry will be different. They'll have different names. Okay. And that's because the molecular geometry only considers the position of atoms, which makes sense. Atoms make molecules. So if you're talking about molecular geometry, you'd be most concerned about the position of atoms. And the molecular geometry will be the same as the electron pair geometry if and only if there are no lone pairs on the central atom. So a good comparison would be methane versus ammonia. So CH4 versus NH3. If you do the Lewis structure for them, CH4 again comes out as we've been drawing it so far, only I decided to use 2 dots for 2 electrons to represent each bond instead of the line that I used last time I drew it a few minutes ago. And NH3 comes out like this. The central atom has an octet of electrons around it in each case, and the central atom contains a single bond to each of the hydrogens in the molecule. But in ammonia, there are only 3 hydrogens, and that leaves 2 electrons left over. And according to the rules for the Lewis structure, those go on the central atom as a pair, a lone pair of electrons. So now we've got a position around the central atom where there's a pair of electrons, but there's no atom on the other side of it. That's going to have an effect when we go to name the geometry. So looking at electron geometry, essentially for the CH4, we have a tetrahedral electron geometry because we have a pair of electrons in 4 places around a central atom, and they get as far apart from each other as possible, and that's a tetrahedron. For the ammonia, we also have a tetrahedral arrangement of electrons because if we're talking about the electron geometry, we're looking at where the electrons are. And there are 4 regions of electrons around the central atom. And I'm going to take the atom off just to sort of show that, okay, we got a lone pair of electrons here in the top position, but they're still forming a tetrahedron, the groups of electrons. The difference comes when we talk about molecular geometry. With molecular geometry, for the methane, the CH4, there are no lone pairs on the central atom, so the molecular geometry is just like the electron geometry. But with the molecular geometry, we don't count the position where the lone pairs are towards the molecular geometry. And so for molecular geometry, you'd go from your tetrahedral electron geometry and basically just completely ignore the position where the lone pair is. So this hole in the atom, I'm going to count that as the lone pair. And it is kind of an accurate representation because the lone pair is right on the central atom. And this is what you're left with. That position where the lone pair is doesn't count towards molecular geometry, and so you don't count it. And so what you have is something that's 3-sided, but it stands up from the surface on which you place it. So what it really is forming a 3-sided pyramid. And so we call this Trigonal Pyramid for the molecular geometry. So CH4, a methane, has tetrahedral electron geometry and also tetrahedral molecular geometry because there are no lone pairs on the central atom. But in ammonia, there is a lone pair of electrons on the central atom, and so it has 4 pairs of electrons total on the central atom, just like methane does. So the electron geometry is tetrahedral, but the molecular geometry will be different because of that lone pair. And what you get when you remove one position from a tetrahedral geometry is trigonal planar, or it's a pyramid, sorry, trigonal pyramid. Trigonal planar is flat, trigonal pyramid is not. Okay, these, as I said before, the shapes can be distorted a little bit because of the difference in repulsions. Lone pairs repel each other more than lone pairs will repel a bonding pair, and that's greater than the repulsion between 2 bonding pairs. So in practice, in the ammonia molecule, the lone pair of electrons will push these hydrogens a little bit closer together to each other. I'm exaggerating quite a bit here just to get the point across, but the hydrogens will come closer to each other and further away from where the lone pair is. Okay. Also, the amount of space occupied around a central atom would be lone pair occupies the greatest amount of space, and a triple bond is actually less than that, and a double bond is less than that, and the single bond is less than that. But the big difference is between lone pair and triple bond. Actually, the amount of space occupied by a triple versus a double versus a single bond, it's a pretty small difference. They all occupy pretty much the same amount of space. It's the lone pair that actually occupies significantly more space around the central atom. And an example would be that the bond angles in ammonia, like I showed a minute ago when I started bending the molecule, would be less than 109.5. In CH4, a perfect tetrahedron, the bond angles are 109.5. In ammonia, they'd be less than that. And we saw the example a little while ago of formaldehyde, where the bond angles in a perfect trigonal planar arrangement would be 120 degrees. But in formaldehyde, because the double bond between the carbon and the oxygen takes up a little extra space, the bond angle between the hydrogens is actually 118, not 120. Okay, figure 19 on page 378, 388 is an important one because it shows you how the electron geometries and molecular geometries relate to each other. And I'm also providing the other table on a PDF that I'm going to post on D2L that's called VSEPR geometries. And I've taken that table from a different source, but I've relabeled the columns in it a little bit that might, in a way that I hope might make things a little more understandable for you. So you can have a look at that also. Anyway, let me get that up here just a second. Okay, VSEPR geometries. This is actually okay, so I finally got that file to open, and I will move the camera so that you can actually see the PDF that I'm going to be posting. And hopefully it'll be a little clearer on D2L when you look at the PDF. But we have a column here where down the left-hand side, we have a column where we see the, actually it's better if I pull it back, isn't it? We have a column where we see the total number of regions of electrons around the central atom, starting with 2 and then 3 and then 4 and then 5 and so on. The first column is what you get if there are no lone pairs at all on the central atom. And in this case, the electron geometry and the molecular geometry will be the same. And it's whatever is written under the figure. The subsequent columns show you what you get if you have one lone pair on the central atom, or 2 lone pairs, or 3 lone pairs on the central atom. And under each figure would be the name of the molecular geometry. The electron geometry in each of these second, third, and fourth columns, the electron geometry would be whatever the name is in the first column. So for example, in this second instance here, where we have 3 regions of electrons around the central atom, the electron geometry would be trigonal planar. If there are no lone pairs, that's also the molecular geometry. But if you have a lone pair represented here by the E, then the geometry of just the atoms is considered bent, because look where the atoms are. So it's bent. But the electron geometry for this bent molecule would still be trigonal planar. So electron geometry, trigonal planar, molecular geometry, bent. And that's how you use that table. Okay, now we can put this back together. All right, and picking up where we left off. Again, for 0 lone pairs, the electron geometry is the same as the molecular geometry. If you have 1 or more lone pairs on the central atom, then the electron geometry would be the same as for the structure with the same total number of electron pairs and 0 lone pairs, but the molecular geometry would be the name given in the figure. The book likes to call them molecular structures, although I prefer to call them molecular geometry, because geometry gives you sort of a more specific idea that you're talking about shape, rather than structure, which is more general. So for most electron geometries, all of the positions are equivalent with each other, and it doesn't matter where the lone pair goes, but that's not true for trigonal bipyramid. So as I mentioned before, trigonal bipyramid, you got 2 types of positions. You've got the 3 atoms that are 120 degrees apart from each other, which we normally draw horizontally, and those are known as equatorial positions. Okay, and the way we usually draw it on paper, it would be like this: equatorial, 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 and then axial would be directly up and down. And so the molecule, as I've drawn it on the paper, is basically this. And as I said before, the equatorial positions are 120 degrees apart from each other, which gives them more space. So the first lone pair will go into an equatorial position, as will the second lone pair will go into another equatorial position. And the third lone pair will also go into an equatorial position. So you will essentially never have a lone pair in an axial position in a trigonal bipyramid electron geometry molecule. An example of one of these would be ClF3, if you want to look at that. The Lewis structure, as for the valence electrons, chlorine has 7 valence electrons. Each of the fluorines also has 7 valence electrons. That gives us a total of 28 valence electrons. And if you draw the Lewis structure, you get chlorine in the center with 3 fluorines around it, each attached by a single bond. And that leaves 4 electrons left over. And according to the rules, we put those 4 electrons on the central atom as lone pairs. And then you check the central, or then you check for octets. We would have already made sure that the fluorines all had octets of electrons. Chlorine has 2, 4, 6, 8, 10 electrons around it, which is more than an octet. But since chlorine is one of the larger nonmetals in period 3 or lower, in fact, chlorine is in period 3, it's big enough to accommodate more than an octet of electrons if it really has to. And in this case, it really has to, because it's bonding with fluorine, which has a voracious appetite for electrons. And so it's not going to take no for an answer, and it's going to make chlorine accommodate more than an octet around it. Okay, so we've got 5 regions. I'm going to change that. Regions of electrons total around the chlorine. 3 of them are bonding pairs or bonding regions of electrons. 2 of them are lone pairs. So according to our chart, if we have a total of 5, and let me get the camera again. If we have a total of 5 regions of electrons around the central atom, the electron geometry will be trigonal bipyramid. But if there are 2 lone pairs, that's 1, 2 lone pairs, means that the molecule itself will be T-shaped. And as it shows you here, well, they've drawn the molecule kind of on its side compared to the way I usually do it. But the lone pairs of electrons represented by the E's, they go into equatorial positions. That would be equivalent to in this model here, the 2 lone pairs would be 2 equatorial positions. And it doesn't matter which 2 you choose, because the equatorial positions are all equivalent to each other. They're just not equivalent to the axial positions. So just take 2 of the equatorial positions off, and this is what you get. And this is what I've drawn here. So basically, what I've drawn here is basically this. Fluorine up, fluorine down, fluorine to the right, 2 lone pairs to the left. 1 here and 1 here. And this is known as a T-shaped molecule. The electron geometry, mind you, is still trigonal bipyramid, but the molecular geometry would be T-shaped. And you can draw it like this. That's why it's called T-shaped, because it's shaped like a T. Okay, and that's the molecular geometry. So for predicting electron geometry and molecular geometry, there are steps. These are given in the book also, so you can look at it there. First thing you do is you do the Lewis structure for the molecule, as I've done in all of the examples I've shown. And then you count the total regions of electrons around the central atom. Remember that one region could be a single bond or a double bond. That also counts as one region. A triple bond also counts as one region, and a lone pair counts as one region. Then you find the electron geometry based on the total number of electron regions around the central atom. 2 regions would be linear, 3 regions would be trigonal planar, 4 regions would be tetrahedral. This guy here. 5 regions would be trigonal bipyramid, the molecule that we just took apart. So it's this molecule here, trigonal bipyramid. 6 regions would be, well, octahedral. And I think I may have mistakenly included 7 regions on the table that I'm posting. You could ignore 7 regions. We're not going that far. Okay, so step 4 would be use the number of lone pair regions to find the molecular geometry. And the lone pairs go into the positions minimizing repulsions. In some geometries, most geometries, it doesn't really matter which position the lone pair goes into. But in trigonal bipyramid, as we just saw, the lone pair of electrons needs to go into an equatorial position. So one of these in the positions that we normally draw going horizontal. In an octahedral molecule, the first lone pair, it doesn't matter where you put it. I could take this atom out and make that the lone pair, and this would be what you end up with. On the other hand, I could choose this atom instead to be where the lone pair is, and it's the same as what we had before. So the positions in an octahedron are all equivalent to each other, so it doesn't really matter which one you use, which position you use for the first lone pair. But if there are 2 lone pairs, it doesn't matter where you put the first one, but it does matter where you put the second one. Because of the extra repulsion that lone pairs have for each other, they're going to want to get as far apart from each other as possible. So if there's a second lone pair, it needs to go directly across from the first lone pair. Okay, and that's what you end up with. So if we have 6 regions of electrons around the central atom, we call that an octahedral electron geometry. If there are no lone pairs around on the central atom, then that would also be an octahedral molecular geometry. If there's 1 lone pair on the central atom, it would still be an octahedral electron geometry, but the molecular geometry would now be what we call a square pyramid. Because if you look at it like this, we could fill in this side and this side and this side and this side, and you would have a square pyramid, a 4-sided pyramid. Okay. The second lone pair of electrons, if there is a second lone pair, would go directly across from the first, and what we would have would be this. It's flat and 4-sided, which would be basically square planar, because it's square and planar meaning flat. Okay, so that's octahedral. All right, some examples. We could look at the carbonate ion. Okay, looking at the carbonate ion, it has a formula of CO3 with a -2 charge on it. So doing the Lewis structure, first of all, carbon has 4 valence electrons. There are 3 oxygens, which have 6 valence electrons each, and there's a -2 charge on it, which means 2 extra electrons. So that's 24 electrons total. We would start out with the Lewis structure by putting carbon in the center and the oxygens around the outside. We start by connecting the oxygens with single bonds, and then we put octets around all of the outer oxygens, and that uses up all 24 of the electrons. We then check to see if carbon has an octet, which it wouldn't. So we take one of the outer electrons and force it to share one of its lone pairs with the carbon. And I chose the one on the top. You could choose any of them. This is a case where you would actually have resonance, and the actual structure would be sort of a combination of the 3 possibilities. Anyway, remember when you move that pair of electrons to become the second part of the double bond, it's not where it used to be, which is why I kind of ostentatiously scribbled it out here. Just to remind you, don't draw it in because it's not there anymore. And this is our Lewis structure for the carbonate ion. For the VSEPR theory, we've got 3 regions of electrons around the central atom. Remember, double bond counts as 1 region. Okay, so that would mean a trigonal planar electron geometry. So it's flat and 3-sided, kind of like a Mercedes emblem again. And there are no lone pairs on the central atom, which means the molecular geometry is also trigonal planar. The single bonded oxygens will end up being pushed slightly closer together because of the double bond, taking up a little bit more space. And so the angle between the double bond and each of the single bonds would be a little bit more than 120, and the angle between the single bonded oxygens would be a little bit less than 120. Okay, and so because I deliberately drew the oxygens about 120 degrees apart, the Lewis structure as I drew it is actually a pretty accurate representation of what the molecule or the polyatomic ion would really look like in this case, because it's flat. Looking at the hydronium ion though, H3O+, the Lewis structure has 3 hydrogens, and each of them has 1 valence electron. And so that's 3 times 1. There's 1 oxygen with 6 electrons, and the positive charge means we've lost an electron. So take away 1 electron. That leaves us with 8 electrons total. We would put the oxygen in the center with a single bond to each of the hydrogens, and that uses up 2, 4, 6 electrons. We have 2 more left, so you put those on the oxygen as a lone pair, and we check for octets, and hydrogen doesn't want an octet, but oxygen wants an octet, and it has one. So everybody's happy. That is your structure for H3O+. We have 3, wait a minute, 4, can't count, 4 regions of electrons on oxygen. Remember, single bond, single bond, single bond, lone pair, that's 4 regions of electrons on oxygen. And that means we have a tetrahedral electron geometry. So one of these positions would be a lone pair. One of them is a lone pair, so you don't count it towards the molecular geometry. So we'll say that's the lone pair. And so we have oxygen is the black atom in the center, oxygen, hydrogen, 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 lone pair, and the whole thing overall has a positive charge. This would be your structure. You can draw it in 3 dimensions, kind of like what I've drawn on the page here, with the wedge being the hydrogen that's coming down and out towards you, and the dotted line being the hydrogen that's going back in away from you, and the straight line being the hydrogen that's sort of in the plane of the paper, or going straight down and to the left. And you'd want to indicate that it has a positive charge also. And so there's your structure, Trigonal Pyramid. And there's also xenon difluoride, XEF2, which we actually saw a moment ago. Oh no, sorry, we didn't. We saw XEF3. There's also XEF2. The xenon has 8 valence electrons, and there are 2 fluorines with 7 valence electrons each. That makes a total of 22 valence electrons in the structure. We start out putting xenon in the center, and xenon is the least electronegative atom present, and also there's only 1 of them, so xenon is definitely in the center. Xenon, single bond to each of the fluorines. Then we would put lone pairs around each of the fluorines, and we still have 6 electrons left. And so you put those 6 electrons on the xenon in pairs. So the xenon in this one has 3 lone pairs on it, out of 5 total regions of electrons on xenon. Single bond, lone pair, lone pair, lone pair. So that's 5 regions of electrons on the xenon. So the electron geometry would be trigonal bipyramid again. 3 of those are lone pairs though. So what happens when you take off 3 equatorial positions in something that's trigonal bipyramid? you end up with this, which is linear. Well, it's a little distorted, but yeah, linear. So the molecular geometry for XeF2 would be linear because of those three lone pairs all in the equatorial positions. Okay. All right, that brings us to okay, that brings us to an example, and my phone's ringing, and I'm over time on this segment, so I think this will be the end for today, and we'll pick up where we left off next time.